There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. This is the last video of this series, video 15. So we talked about the self-interacting field theory and the gateway to Grand Unification Field theory. So let's do a summary, okay, what we have done so far. The self-interacting field theory unifies quantum interaction, strong interaction, and gravitation together into the same equation. Okay, so it also unifies the microworld and macroworld. That means it's the same physics law for macroworld and microworld. So we don't need quantum mechanics for microworld. Quantum mechanics also applies to the macroworld. Okay, the same theory. So the other unification will be electromagnetism and the weak interaction. So basically, the unification will be this SQG, strong interaction, quantum interaction, gravitation, and the electromagnetism, weak interaction, unified together. So what I think, this is relates to the rotation, okay? This is relates to the energy and momentum, okay? So why I said that the self-interaction field theory unifies the microworld to the macroworld, okay? In the beginning of the video, we made some assumptions, okay? So we made the assumption that G is inversely proportional to 1 over R, because that's gravitational field goes out and come back, okay? That's the second question, or the number 2 question we asked, okay? We have the self-interacting term means the gravitation constant is inversely proportional to the G00 of the, or time metric, okay? Time metric of Einstein's relativity, okay? Because of that, we have 2 solutions which has a scale difference by 10 to the 39th. That's what we call Dirac Large number hypothesis. Okay? So these 2 assumptions, one is the field self-interaction, another is field travels and come back. So that's the foundation of Newton's law of gravitation. Newton's law of gravitation, F equals G m1 m2 divided by r squared. Okay, that's the surface density. That's the mass 1. That's how much field emitting. Mass 2, it's how much is taken, or vice versa. Okay, so the implication of this self-interacting theory is that the object has boundary, and the field can be trapped, bent, or focused. Okay, so that's a direct implication of the theory. Okay, but if we study the microworld, we are outside of the boundary. Okay, if we look at the microworld, because we're bigger. Okay, when we look at the microworld, we're outside the boundary. Particles can only interact through equator. All quantum mechanics properties are explained based on self-interacting assumptions. Okay, and the quantum mechanics is a phenomenological model of microworld. So it's not the complete theory. So based on this, what do we see that? The self-interacting field theory does not allow electron to further emitting electromagnetic waves to lose energy at the ground state. That means once it's lost to the maximum, already lost, they cannot lose anymore. If they lost, then they lost its balance. So this is why if we see the macroworld, we have an electron movement. Let's say an electron like electron move like this, it's emitting radiations, okay? The electromagnetic wave being lost. If this is a charge, okay, if a charge, that's current. You have charge movement, you have a current, then you produce radio waves, okay? But the electron rotating around the nuclei, they don't emit radiation at the ground state, because that's the minimum energy they have to keep. They cannot lose it anymore. This is why the electromagnetism for the large scale or macro world and micro world is the same phenomenon, but the energy cannot be further lost. That's why the micro world is different. It's not because the law needs to be changed. It's because the self-interacting field start coming into play. Okay? In the macro scale, the self-interacting field theory, it's not that strong. This is why we see our macro physics. When in the micro world, the self-interacting field became very strong. So you cannot ignore that. That means the electron charge cannot lose energy anymore. Okay? Because the self-interacting fields start coming in. If we study the macro world, we're inside the boundary. If we study the universe, okay, we're inside the boundary. The self-interacting Newton's law of gravity and current general relativity is fine, okay? You can explain a lot of things. But the self-interaction modified general relativity should be able to use in the micro world and macro world because they have gravitation and quantum mechanics all in the same equation. This is why the self-interacting general relativity will be our final unification theory for strong interaction, gravitation, and quantum interactions. Maybe even more. The force beyond our universe. Maybe have another layer of force. So basically, from the universe scale to the micro scale, the same equation can be used. Because they're the same theory, this is why we can use Hawking theory of relativity to predict the mass of pion nucleon as well the lifespan of pion. Okay? So that means we use the macro scale theory or modify the general relativity to describe the micro world. So that means the self-interacting field theory unifies the macro scale and micro scale. That's what Einstein has been trying to find, okay? Got right only one equation. This is the equation, part of the equation where we're going to be able to unify the macro world and the micro world. So let's come back to the current physics. What's missing, okay? So the current unification scheme we have, its heat and work are related, okay? This is micro world, okay? Energy. But then the work is macro scale. The heat is micro scale. When we feel something hot, okay, that's the heat. Okay, that's the micro world energy. But we can measure it in the macro world also. We can use a thermometer, measure the micro world energy. Okay, but this is good. This is good unification. Magnetic field, electricity are the same in the Maxwell equation. Mass and energy the same. We didn't say, oh, okay, the table's mass equals mc squared. But the electron is not. Okay, Einstein's E equals mc squared. Micro world, macro world the same. Okay, because the macro world is made of micro world. So when the nuclei lose its energy, when they reaction, strong interaction, or the nuclei reaction, they lost mass, they lost energy. Okay, so there is no micro world and macro world physics. You see, all these successful unifications, they are both micro explanation and macro explanation. This is good unification. Okay, But the current micro scale, we have electromagnetism and then weak interaction. Then there's no marker word, okay? And electromagnetism, weak and strong interaction, no marker word. Quantum mechanics, no marker word, okay? But people say, hey, Q, the micro word, because h is so small, the Planck constant is so small, we didn't see it in the macro word. We will see why, okay? So the next one, the current physics, electromagnetism, weak interaction is no macro scale under the micro scale, okay? They add a strong interaction into the equation. The current physics, okay, you have Newton's law of gravity and you have general relativity, but the micro scale, okay, you have the macro scale, all these tests. The micro scale we cannot test because it's so weak. So weak, we cannot test these. So we're successful on this, okay? So the Einstein's relativity already bring the nonlinear term, okay? Already have nonlinear term, but we know he missed the scalar or self-interacting term. Einstein missed that. So let's come back to the question we asked. So what we did in this video, we talked about the current self-interacting field theory was able to unify the macro scale and micro scale. We have currently also very successful unification which apply to micro scale and macro scale. Okay, so now we back to our original question we asked, the 6 questions. If there is a black hole, what comes out of the black hole to attract, okay? Attract the material outside the black hole. Nothing comes out, so no attraction, okay? That's the conclusion we have, okay? So if the field goes out from a source, does it come back? Yes, there is a boundary, okay? Does electron, photon, and quark have internal structure? Yes, okay? What force is binding the energy of electron charge and spin together? Self-interactive field to all level of particles. Photon, electron, nucleon, quarks, or whatever, okay? So can strong interaction reach to the macro scale? Applying the still that, yes, the strong interaction, what I call is self-interacting strong interaction. It can reach to many scales, okay? Strong interaction, okay? But it's can only reach to a certain time. This is why E equals h bar v, okay? So when the energy is so big, the v is very quick. That means the more energy you try to reach out, you need it, but then the frequency will be much higher, very short time, okay? That's in fact, it's quantum mechanics, okay? Is quantum mechanics complete or is only intermediate description of quantum behavior? Until we find the generative version of the quantum mechanic field, the motion will be predictable, okay? So basically, based on the self-interacting field theory, if we find the quantum mechanics spacetime, okay? The quantum mechanics spacetime, that means quantum mechanics and okay, quantum mechanics, okay, and relativity are writing into the same equation because quantum mechanics is also a general relativity, okay? So the electron movement, the microparticles will be predictable. So the self-interacting field theory unifies gravitation and quantum mechanics together by a Dirac large number hypothesis. Dirac large number hypothesis, okay? That's a 10 to the 39, okay? Because quantum mechanics, it's a self-interacting Newton's law of gravity. That's the field equations. That's the quantum interaction equations. It's clearly quantum potential. It's a self-interacting potential, okay? They are different by h bar over m and gm, okay? That's 10 to the 39, okay? Yes. So what we did is the self-interaction is able to write the quantum mechanics interaction into gravitational self-interacting Newton's law of gravitation. They are writing into the same equation. We already showed that in the self-interacting general relativity has two solutions. One is strong interaction, one is gravitation. We already see in the previous video. Okay. The self-interacting theory also unifies that quantum mechanics. It's a self-interacting strong interaction. Okay, they are the same. They are equal. So that means gravitation, it's a smaller, 10 to the minus 39 smaller than the strong interaction. But strong interaction, quantum interaction, they are the same thing. Okay, why is that? Because the uncertainty principle, we have something like that. Okay, if we rewrite the uncertainty principle, we have h bar c over here. That's a quantum interaction. Okay. So the strong interaction we can write like that, but as the boundary, then we can rewrite the force like that. Okay, the total force will be like that. We see strong interaction, quantum interaction, they're the same. I mean, delta x, it's r, the distance, the reach out. This is our r of the rotating strong interaction. They keep reaching out to different distances. Okay, so they are the same strings by h bar c. Okay, what's interesting is that self-interaction, strong interaction, it's the same as quantum interaction. That's why the strong interaction fine structure constant, strong interaction constant equals 1. Okay, why? Because they are the same thing. Okay, if you are in particle physics, you know that people always talk about strong interaction coupling constant. Coupling constant. Okay, coupling constant equals 1. Okay, so what we have, the self-interaction unifies the macro scale to the micro scale, unifies the quantum mechanics, strong interaction, and gravitation into the same equation. Okay, and the strings already described by this. Okay, so there is another constant which most of physicists know, that the fine structure constant. Okay, the fine structure, that's an amazing constant. People always asking, hey, what's going on here? Okay, so we know that the quantum mechanics interaction is like that. Okay, but we know the electron charge force, it's like that. So the fine structure constant, it's a electromagnetic force over the self-interacting strong interaction. That's that. Okay, we see that the E squared divided by this. This is why the fine structure constant, it's like that. Because fine structure constant, it's the charge force over the self-interacting strong force. They are different by 1 over 137. So that means the strong interaction is 137 times stronger than the electric charge. Okay, so that means the quantum interaction, it's the strong interaction reached to the macro scale or the bigger scale than, or 10 to the minus 10 meter. Okay, that's our quantum mechanics scale. That's where it reached to that. Okay, but the electric charge, that's why it's called fine structure constant. In the quantum mechanics, you have different wavelengths, different structures of different particles. This constant always appears because the elementary particle has charge. Okay, they also have strong interaction, okay? What I call self-interaction, strong interaction. So basically, what I'm saying over here, the electromagnetic charge force and the strong interaction force, the ratio is 1/137. That defines all the quantum mechanics structures. Okay? This is why this constant is also very critical, because that's a scale where the strong interaction can reach to the quantum scale, and also the charge also kind of strong. But only, unfortunately, the gravitation is weak. Okay? We have the self-interaction, strong interaction, and charge quantum interaction, because self-interaction, strong interaction, it's the same as quantum interaction. So now what we would like to explain the Dirac large number hypothesis, okay? Or some people call Dirac large number principle, okay? Dirac found this theory or the coincidence, and he doesn't know why, okay? Now we're trying to explain why, okay? For all the numbers, the radius of the universe divided by the radius of the nuclei, 10 to the 39. Because, remember, we have G proportional to 1/r. That's why the radius of the universe, the larger the r, the smaller the ratio, okay? Okay? And the radius of the nuclei, because the larger the radius, the weaker the gravitation constant, because it takes time to come back, okay? So this is why that's easy, okay? The first coincidence we have. The strong interaction strength over the strength of gravitation, that's Gs over G that. Okay, we already derived that, okay? So the universe lifetime divided by ion lifetime, because time equals the radius divided by speed of light. Because the microworld travel at the speed of light, the macroworld also travel at the speed of light. The radius ratio is their time lifetime ratio, okay? So we see that, that's already explained. The mass of the universe divided the mass of the nucleon is 10 to the 78. What we have over here, that's our boundary condition for the nucleons. Okay, that's our boundary conditions. That's our boundary condition for our universe. Okay, they are both equal 1. The microworld, the boundary, it's the constant times mass divided by RC squared equals 1. 1 equals 1. Okay, both equals 1. But if we rewrite these, we'll see that Gs over G, that's the strong interaction constant divided by the gravitation constant, times Ru Rn equals Mu Mn. Because Gs divided by G, 10 to the 39th, okay, the radius of the universe divided the radius of the nucleon is also 10 to the 39 times 10 to the 39, okay, equals 10 to the 78, okay? So that's something like that. It's so simple, okay? So the last one, we have the quantum interaction over gravitation. We already talked about. If we divide the mass, okay, we know that that's in the end, it's a strong interaction constant over the gravitation constant. Because we have this scale, we can use the gravitational physics, okay, or Hawking theory to study black hole. We replace that by a constant. Just change one constant. That means we change G to Gs. We change G to Gs. We change G to Gs. That means we can use Hawking equation, the macroworld approximation equation, okay, to calculate pion lifetime. Yeah, the microworld. Because they're all different by a scale of 10 to the 39. So all those guys who studied black hole theory, thank you. We can use this theory to study the nuclei interaction. okay? Because they're all different by a Dirac Large number, okay? The scale. If we change that number, we have a new theory, okay? So that means God only write one equation. God can write for gravitation of the universe. God can also use the same equation for the microworld, okay? So the self-interacting field theory unifies that because they are different by 10 to the 39, okay? It's not only because their scale different. They are in the same equation, okay? Because it's nonlinear, okay? They're in the same equation, just two solutions. So that means gravitation can convert into strong interaction, create particles, okay? Particle can emit in the waves or radiations out to the universe. And in the end, the universe trapped all the energy together. That's a Dirac Large number hypothesis. Now let's see what the Planck units, okay, what look like. The Planck units, what look like. When people study the black hole, okay, or the Big Bang theory, they are not sure what's going to happen in the early universe, very early time. So what they play with the different constant. In the end, they come up with some scales, okay? The Planck scale, the length, we see that. That's 10 to the minus 35 meter. But our so far smallest scale is 10 to the minus 15, okay? So what do? We have the older expression for Planck length. We have the results. We have a new expression. What we did, we just replaced the gravitation constant by Gs. Okay. What we got? We got 1.5. By the way, this is nucleon radius. Okay. So that means when people play with Planck constant in the early universe, the early universe may be only nuclei. Okay. So they're not like this. So the Planck time, we have this 10 to the minus 44 seconds. It's crazily small, okay? The length is also crazily small. The time is also crazily small. Because, I mean, you divide by c. You see that they're divided by c. So now if our length increase by the order of 10 to the 20s, we also have something like that, okay? So that's the Planck time, which is about 10 to the minus 23 seconds. By the way, that's the strong interaction constant, or pion shelf life, pion lifetime, okay? Or strong interaction time scale. Strong interaction time scale, okay? Okay, that's a strong interaction time scale. I don't know what's this time scale, okay? It's different by 10 to the 20s. Okay, I don't know that, okay? So the Planck mass, if we rewrite this is kind of big. But you see, time is small and the length is small, the weight is high. If we replace by that, okay, what we got? We got the nucleon mass. By the way, this is the pion mass, okay, sorry. Yeah. So you see, our scale, our length, it's our radius, okay? Our time, it's our interaction time. Our weight, mass, it's our pion mass or nucleon mass, okay? So, I mean, you have the Planck temperature, okay? It's very, very high, okay? But this is our nucleon temperature. So you see that. So now the self-interacting theory, it's able to put strong interaction and gravitation into the same equation. They're only different by a scale, okay? So I think the current Planck units are mismatch of scales, okay? Why I think so? Because if you study universe, if you study the gravitation, okay, you study universe, you need to replace the Planck constant by the universe Planck constant. We don't know that. We may measure it, okay? That's the angular momentum of the universe. Okay, if we put a much bigger number of h, this one will become bigger because it became bigger. Okay, if h become bigger, this one become bigger. If h become bigger, this is even bigger. Why? Because our mass of the universe is big, much bigger than this. Okay, this is less. It's very tiny. Okay, it's some weird scale. Okay, because there's no particle like that. It's a few milligrams. Okay, there's no elementary particle like that. Okay, there's elementary particle like that, but not elementary particle like that. So if we now put this one much bigger, we also have a much bigger weight. That's maybe stars or our solar systems, something like that. Okay, we don't know that until we measured the h for our universe. When you mismatch it, you get some weird constant. Okay, so weird scales. This is totally nonsense scale, I think. Yeah. Okay. So unfortunately, if we think the self-interacting theory, the current theory, is good, then anybody who studied the Big Bang, sorry, you have to redo the calculations. Okay, yeah. So the Big Bang for the nuclei, that's a Big Bang for our nuclei. Yes, our nuclei keep creating and keep disappearing. That's like our micro universe. Okay, I mean the scale is very clear. So we think we need a new h for the universe. Okay, in order to do that. So based on these last 3 slides, we already described the fine structure constant. That's the electric charge over the strong interaction. The Planck unit, that's a nuclei scale. The Dirac Large hypothesis is the scale of the gravitation over the scale of strong interaction. So up to now, our physics start make sense. Okay, if we don't have the mismatch, we already have a new scale. Okay, this is much more interesting. Okay, the future PhD videos. I mean, this is for people who have some background in physics, who are entrepreneur or investing in physics, or some freelancer, or just some fun for physics. Okay, in the future, we're going to present some computer simulation of different scale of self-interacting field theory. We're going to get into the technical details. Okay, what we do in the future videos, we're going to talk about the quantum mechanics, space-time structures, because we now have the self-interacting general relativity. We can see what's behavior of the black holes. Okay, then we will be able to derive the space-time of the smaller black holes, how it behaves, based on the self-interacting general relativity. We're going to also spend more time on the self-interacting general relativity, different solutions, but we have to get into the mathematics, very complicated mathematics and derivations. So basically, if we know these two, we can do the nanoscale. Okay, because the nanoscale is a problem. You have the outside of elementary particle. All elementary particles or the self-interacting particles start reaching together. For example, when we have the elementary particle, the self-interacting strong field reach to 10 to the minus 10 meters, okay, then in this kind of scale you have different molecules. How the energy propagates from one particle to another particle, or one molecular, or we call molecular level. Okay, because the current physics, they cannot do that, because once you get into 10,000 identical particles or 100,000 identical particles, you don't know what to do. Okay, even you have identical particle theories, but there is no theory can do the final calculations. Yes, you have some proposals, okay? But now we have this. We can do the nanotechnology based on the quantum behaviors. We may be able to see how the self-interacting wave propagates among different molecules, okay? So once the multiple molecules start affecting the nuclei movement, so that's where we have practical applications, okay? So in the last slide, I want to propose another hot topic. It's about the quantum entanglement, okay? We would like to propose that a double slit experiment of self-interacting field theory, because currently people think elemental particles are wave and particle duality. They can have wave and particle properties. Yes, we have the self-interacting field and particle movement. So the self-interacting field may be a wave, okay? So how it behaves, because now the quantum mechanics, it's statistics, but the current quantum mechanics, it's statistics, okay? Okay, so the self-interacting field theory, it's determined, okay? Determined, okay? Okay, so determined. Now these two philosophies, they are incompatible, okay? So which one is correct? Because our quantum mechanics now, it's already going to be replaced by the self-interacting general relativity, okay? So what we say over here, so whether it's predetermined, because people say, hey, we have the double slit experiment which claims they can interfere the particle already passed, they can interfere the future or coming particles. It's not true, okay? What I'd like to propose that the double slit itself remembers the past interaction. This is why you have the interference, okay? But the self-interacting field theory thinking the interference property are from the property of neighbor spacetime, okay? So if you have the field particle goes through, you move the slit particles to a certain level, okay? But that level being remembered by the slit, okay? So now if the double slit is removed, you have one photon pass through, and remove the slit, and then have another new slit come in, it doesn't remember what's happening. But the quantum mechanics said, hey, statistic, we don't care, okay? So now if somebody can do the double slit experiment, and after one photon pass through, change the slit, I mean, you can have many slits. You can have automated, keep going, move to the next one, okay? You have a slit very long, or in between, you cut it into pieces. So one photon pass through, move a slit, one to pass through, move another slit. I assure you, there will be no interference. So whether the self-interacting theory about the elemental particle is correct, or the quantum mechanics is correct. So now let's have some physicists do this experiment to prove if there's no interference, because quantum mechanics didn't say, okay, the double slit as long as they're identical. They don't say, okay, it's statistics. Now what I'm trying to say over here, self-interaction said, okay, it remembered, because the interaction remembered by the slit. Now if I change the slit, the interaction will be taken away, so there will be no interference, okay? So this will be a very critical experiment to prove the self-interacting field theory may be able to replace quantum mechanics, okay? I mean, based on the self-interacting general relativity, we can derive the quantum behaviors. That's mathematics. We're going to try to be coming close to replace that. We will derive the quantum mechanics but in the end, philosophically, they are different. Okay? So these 15 videos I would like to dedicate it to Albert Einstein. I think in the end, these videos shared all the thoughts he has. He doesn't like quantum mechanics. He wants to do unification field theory, okay? And he likes general relativity, that's for sure, okay? So now what I did is I rewrite general relativity into a tensor format, okay? So I think if you read a lot of literature about Einstein, this is his continuation of his philosophy, okay? Thank you for watching these videos. Okay, thank you.